So welcome everybody. My name is Andreas Poller. I'm from CSD Engineers. I'm very grateful to be able to present our work here. I would like to take the opportunity to thank my colleagues who collaborated in this project, colleagues from NAGRA, from CSD, my company, and also from Intera. The talk is on a special thanks to Irina, who initiated the project at NAGRA. It's an R&D project, so we are still underway. The talk is on optimization, of course, and we look at the thermal aspects of a generic high-level waste repository through Pareto front analysis or Pareto analysis. There are many aspects that we've already heard so far yesterday and today, so you will recognize many bits and pieces that we are already familiar with now, except for the Pareto analysis. This is something new that we haven't heard yet, so maybe you're still interested in that. The talk itself is structured in a very classical manner. I give you a bit of a context because context should be clear now. Then I'll talk about the approach that we are using, that we are applying, that we not develop but kind of modified to adapt to our problem at hand. I will talk about the results of an example application that we did in the NAGRA context, but on a generic level. And finally, I will give some conclusions from the current project stage. So context, background, and aims. Here I can make it short. We had the talk from Matthias Braun yesterday. So you know that now Switzerland is able to focus on a site, and there will be general license applications. And there are robust repository concepts around that will underpin this license application. And then, we heard this several times before, then there will the design and optimization phase, which will then finally lead to the construction license application. With discussions we had, we found that there may be a need for a methodology because we have so many. It's a complex project. We have many stakeholders, and the stakeholders have different interests and attitudes and so on, and there might be conflicts of interest. And we have heard this already also, that optimization is about finding compromises and balancing things out. So this is the same thing here. So it's about resolving these conflicts, but not only resolving them, but you also need to be aware of them. You need a methodology that identifies these conflicts, that resolves them, and last but not least, it's also important to communicate where the conflicts are and how you manage to resolve them. So we started, NAGRA initiated an R&D project with the aim to develop a workflow. We call it the Repository Optimization Workflow, or short ROWO. You will hear this a couple of times. And the aim is that this workflow will be ready once the license is, or once it is needed by the main design thread of the NAGRA engineering team. So a bit of a context. These are the requirements that we identified on the ROWO. It's kind of similar to the principles on optimization that I think it was Stan Galson yesterday. He established some principles, and these are very similar, the requirements on the ROWO. So first requirement is that it should be multi-objective. I said already we have different stakeholders. You all know that. So and the stakeholders have different needs and wants and so on, and we need to be able to integrate this in a framework so that we can effectively work with different objectives of different stakeholders. The second one we also heard, I think it was Andra, but also others, the POSIBO, the Finnish program. It's important that you have something that is cross-discipline, that you can work with apples and chocolate. So you cannot compare apple and chocolate, but you can trade them, and it's important. It's about trading, making trade-offs, making compromises, and so we need something cross-discipline. Quantitative is important. I think at one stage, if your program steps from the feasibility stage or the siting stage into the design and optimization stage, and then you may realize that lots of things that you take for granted are actually based on qualitative argumentation. And suddenly you think, well, actually we should judge this or tackle this, whether this is also ready in a quantitative world. So increasingly, and we heard this from the Finnish program and also from SKB, that the quantitative aspect comes in when you start thinking about operation and design and construction. Multi-level means that we would like to have an approach that works and is valid on on the holistic level, as Ingo just introduced, but it should be also be applicable to the optimization of an individual component. So this is maybe a very high requirement, but we think we have something that fulfills this requirement. This also ensures that your approach is consistent and you end up with a consistent design for the repository. So this is important. Transparency is, I mentioned it already, it's about communicating. It's important that the stakeholders, the regulator and the local population, they can see and understand how you did that, how you arrived at your compromises. So transparency is key. And last but not least, the approach must be efficient, because if it's so expensive to find your optimization potential, it might not be worth the effort. So you have to be able to come up with a practical approach. So on the approach, another definition of optimization. Until this morning, I thought, well, you might think, well, why do you tell us? It's so clear what optimization means. But after the talk of Christoph, maybe you all agree that it's maybe not so easy. So I come up with this definition that I found in the dictionary, and I like it because it presents the main building blocks of optimization. So the first thing is it's a process. It's a continuous process. We've heard that before. That's easy. The something is a bit more tricky, because it tells you need to think about what do you want to optimize. Do you only want to optimize the repository or a single component, or do you want to expand to also include the pre-disposal waste management system? Andra told us that there is maybe lots of potential there if you enlarge your scope, and this is also what we observe. So something is about the system you optimize, and it's important to make clear boundaries of what you're optimizing. Good is related to who you ask. So it's about the stakeholders, their interests, needs, attitudes, whatever you call it. It's about requirements, it's about objectives. I will use the term objective in the following. And this is tricky because, as I said at the beginning, there can be conflicts of interest, and you have objectives that you need to trade and so on. And finally, last not least, possible. It tells you about the constraints. And here we, as constraints, we take the natural and the technological constraints. In contrast to what Lucy said before, we strive at not defining requirements as constraints, because we think it's very important to first find out what is possible and then to ask what is desirable, because then you can really see the limits of what is feasible, what is possible according to the natural laws and the current technology. And then you can also include the stakeholder requirements. And the reason for that is that you cannot go to physics and negotiate the laws of thermodynamics, but you can always go to a stakeholder and say, well, is this constraint or is this requirement really so hard, or can we relax it a bit? We heard this yesterday, that sometimes, especially when you come from the feasibility stage, requirements may be overly conservative. Or from the Swedish, we've heard that it may be not even a requirement, but just an assumption that has survived several decades. So we think it's important to distinguish these two aspects. It's not always easy, but at least we strive at that. So on the approach, this is a kind of circular approach. We start at the upper left corner. It starts with the system understanding at NAGRA. It's, I think, in every organization over the years, lots of body of knowledge, huge body of knowledge has been built up. And this is important because then if you start to look at what is important to you, so you can call it the success criteria. This is the starting point, but it's missing here. But it's what is important. You need to define it, and then you can ask the experts in your organization or your contractors and telling you, so what is really important with respect to these key requirements, and you will end up with a list of key factors. This is similar to the success factors we heard yesterday, but not quite the same. You come up with a list of key factors that you know from sensitivity analysis or experiments and so on. And you can divide these key factors into two things. The one are the key constraints, those that you cannot really or practically modify, and you have the key choices. This is the factors where you have a certain degree of freedom to choose from different alternatives. Then the next step, going clockwise, it's about configurations. It's always about different combinations of alternatives, so we call this configurations, and we generate many of them. Yesterday we heard Andra had about like 100 different design modifications. We have about 1,000 here. And because we have so many, we cannot be very detailed, and this is why they are of a rather stylized nature. But they are suitable for our purpose, so we generate many stylized configurations. This is easily said, but not so easily done. It's about programming and bringing all the information together. Then in the next step, let's have a look at if this works. Does this work? No, it doesn't work. So the next step here is at 4 o'clock, it's the assessment. So you assess against the objectives of interest, your success criteria with assessment models. So this can be very simple models or a bit more complicated models. But again, since we have so many configurations and the level of maturity of these configurations is not so high anyway, we are okay with relatively simple models to assess against cost or stakeholder acceptance or environmental impact or whatever you're interested in. From that, we use these results from the assessment and then we do the Pareto analysis. I will explain this in more detail later on, and hopefully you can then identify an optimization potential. And once you have that, then you need to go back to the real world. This is what I also recognized in Andras' presentation. They had so many possible modifications, and then comes the point to go back to the main engineering division or the main engineering thread and then challenging these new insights that you have gained with the application of the robo. Because you're in a very stylized world, and what you find out might not be true in the real world if you have a full design of a full repository. So you need then generate few realistic configurations, or you modify your existing one, and then you use the models that you use in everyday life for design and cost study, and you assess these modifications. And from all that process, you don't get an answer what is the optimum, but you learn a lot. You learn why configurations are better than others and why this is the case. And this insight, then you can transfer to the main tasks that you do and to support the optimization efforts that you have at NAGRA or in your organization. So we will proceed with an example application. We will look at a generic repository for high-level radioactive waste. So this is still an RD&D project. We are not optimizing the Swiss waste management system. In the title, you heard that we look at the thermal aspects. So we need to have a look at those wastes that emit heat. So it's spent fuel and vitrified high-level waste. And we optimize with regard to 3 indicators. The one is the evolution of temperature post-closure in the near field. The second one is the evolution of pressure in the clay host rock due to thermal expansion of the pore water. This is also an important aspect of clay rock systems. And we look at total cost, and we try to identify whether there are conflicts of interest and whether these can be resolved and what can be learned from that. So just shortly, I will not read through all this, but as I said before, for thermal aspects, we need to go beyond the repository. We need to look at the predisposal waste management systems. These are the main key factors that we identified, distinguished between key constraints on the left and key choices on the right. It all starts with the waste. Lucy said it, the characteristics of the waste is so important, so it's the main key constraint, but also the existing nuclear landscape in your country and also the cost of that nuclear landscape. Maybe the annual cost of interim storage facilities is a very important factor, and in your country at least it's in Switzerland. Key choices is clear. When do you start? How do you package the waste and where do you do it, and so on. The repository part is the same. We have also some key factors. The most important, it's also on the left, we have the key constraints, and on the right, the key choices. Key constraints is the space that you have in your site, or possibly in your site. You have the conditions, the THM conditions, technology, materials available, and so on. Also, again, unit prices for building tunnels, and so on. Key choices is how you put the canisters, or in which order you place them, and also in which rate. The situation in Switzerland is different to the situation in Finland, because in Switzerland the nuclear power generation will be over, whereas in Finland it will be a parallel process. So here in Switzerland, canister emplacement rate is more important than in Finland. And now let's dive a bit more into the detail. This is maybe an overloaded slide, but since this is a scientific conference, I think we can go through that. And what you see here is a combination of the thermal characteristics of the two waste types and the packaging strategy. And on the x-axis, you see the different canisters. On the y-axis, you see a measure of the thermal load of the canisters. This is expressed in a hypothetical temperature rise. You can also think of like a thermal power. It doesn't really matter here. And then you have several possibilities how you want to package your waste. And since we wanted to step back just to relook from the beginning and try to see the limits and where we are within these limits of the design space, we also look at the extremes. And the most extreme one is the black curve. It's a very easy idea. Just think that you take the hottest waste you have, and then the next hottest, and you fill up your canister, and then you go on like this, and then you end up with the black curve. You have a few canisters that are very hot, and then it suddenly declines, and you have 90% of the canisters that are much different to this 10%. And you might say, why do you do that? This is so stupid. But again, in this first initial R&D stage, we want to look at the extremes. And this is a packaging strategy that gives us an extreme. By contrast, look at the green line. This is a very common approach, is that you establish an interface requirement between your predisposal waste management system and the repository. For example, Nagro has adopted about 1,500 watts so far. This would be a limit for the thermal loading of the canisters. And you can do that. You see that when you follow the green line from the 0 to the 1,500 canisters, that you can fill them up very efficiently. But at one point, you have to admit that there are gaps in your canisters. And in contrast to the black line, you will end up with a few more canisters than in the black line. So there's a difference in total number of canisters, and this is important because canisters are costly. If you have more canisters, you need more tunnels and you need more time. So there is also something in between. For example, the red line. There are also other possibilities, but we try to span the range. So we try to come up with very extremes, but something also in between. The red line is also very easy. You take the hottest and then the coolest, and then the next hottest, and then the next coolest. And this kind of is a balanced approach. So you don't have so many very hot canisters that will heat your repository dramatically, but you have just a few. You see you have a few red, maybe 500 canisters that are hotter than the others. And maybe the idea is that maybe by looking at the entire system, that by adapting your canister spacing underground and your tunnel spacing, you can compensate for that, for these few number of higher canisters. This is an illustration for a canister with a medium-sized canister. We look at different canister sizes. This is the size M, medium. This is equal to the current canister size of many canisters that are around diameter of 1 meter. But we also have different sizes of canisters up to the size of transport and storage casks. Good. Then I said we generate many configurations. We do that in an automated way. This is all scripted. These are 2 examples of the 1,200 configurations that we created. And the most important parameter here is the canister size. This is indicated here. We have on the left, we have small canisters. This will lead to many tunnels and, of course, a large disposal area. And by contrast, on the right-hand side, we have a packaging strategy with extra large canisters. And then, of course, you have much less tunnels. And obviously, this is more cost efficient. We also look at access structures. So this needs to be deserved. We also try to look at the constraints that, timing for construction, parallel operation may be an issue. We tried to integrate that, but not in all detail that it's engineered in a real program. So these are 2 example stylized configurations. We have many of them, and with many different combinations of different design alternatives for the design variables or the key choices. And this is what comes out. This is one of the main results, but not the only one. This is the outcome of the so-called Pareto analysis. Maybe we start with the axis on the x-axis. So the horizontal axis, you see a measure, an indicator for the total cost. It's not the total cost, but it's the total cost for our specific project. And on the y-axis, you have a measure for the temperature in the near field. So we are interested in the maximum temperature close to the canister. And here, the many dots are the results that we calculated with the simple assessment models for the stylized configurations. So here you see the results for about 1,000 configurations. And not surprisingly, if you look at the colors, the green configurations have a small canister size, so you will have low maximum temperature, and the blue ones are the extra large canisters, and of course you would heat up the repository dramatically. So why do we do that? You may think, well, 300 degrees Celsius is out of anything, so even Hotband is not looking at that. But as I mentioned before, we are tried to, as SKB did, we tried to restart a bit and to look at the extremes. We wanted to know the extremes, we wanted to know the limits of the design space, and actually also see where the current configuration is located within that design space. In an ideal world, what you would all wish for Christmas is that, or whatever, is to end up in the origin, to have a repository that has no cost. 5 minutes left. I will speed up, and that is cold. But that is not impossible because of the conflicts of interest between, let's say, the money or the stakeholders that care for the money and the temperature that is an indicator of post-closure safety. So, and this Pareto analysis tells you how close you can get to this ideal point, and it's marked here with a red line. And this is what we are aiming at. We want to see the limits of the design space, and moreover, to see where we are and where we could possibly go. The large circle in the lower left corner is a surrogate of Nagra's current reference configuration. You see that it's very close to this Pareto front. So as I said at the beginning, Nagra's concept is a robust one. It's sufficiently optimized. There are still margins, so there is a good position to proceed from that further. And we see that there are some configurations that are similar in thermal performance, but they're a bit cheaper, and the cost difference is not nothing. So we thought, well, we found something. Maybe this is an optimization potential, but now we have to go on in the circle, and we have to look in more detail. So then we started a so-called benchmarking. We tried to confirm what we find out with these stylized configurations and the simple models, whether this is also true with the detailed models that we have for a more realistic configuration. Here is this more realistic configuration. You see that it has very few emplacement tunnels, different to what you may be familiar with from Nagra pictures. So we have long emplacement tunnels because this is more favorable for heat dissipation into the rock. We also have a spacing between the tunnels that is not equidistant. We have the outer tunnels are further away, and this is because the hottest canisters are at the outer fringe of the disposal area. We assume this packaging strategy E. You remember the red one, the hot and the cold and so on. Still theoretical, but to try this out. And the canister positioning, I already said about the tunnel spacing and the canister spacing. We didn't detail a detailed assessment from several aspects. There was detailed numerical calculations with TUF3 by our colleagues from Intera, and they found out that the TH performance is actually quite similar within the bandwidths that you have and the sources of uncertainty, that it's actually quite similar. So this kind of confirms what we saw in our stylized world. And we also did a detailed cost estimation, and there are two parts. The cost saving for the repository part were more or less confirmed, but we have not yet looked at the cost optimization potential for the predisposal part. And as we've heard already yesterday from Andra, it might be there, but you have to prove that it's there. So this is my last slide, conclusions. So the overall goal was to develop a workflow. We did that. We developed it or adjusted it, and we tested it with an example application. This is already the third round, so it seems to work, and the optimization potential is quite stable. So we are increasingly confident that this is maybe true. The ROVO, the workflow, is in line with the main requirements that we identified prior to starting the project. And we saw a major conflict of interest that you saw with this Pareto front. There is also an absence of conflict of interest when you look at the pressure in the host rock. But we found some optimization potential, and the results could partly be confirmed with more detailed studies. So an outlook, the next step within this RD&D setting, still in a protected world. So we will include additional constraints, and obviously the most important one is now, since NAGRA is focusing on a given site, we'll of course include the properties and the space available in this selected site, and also the decision on the location of the packaging facility. This is now decided. We can use the design variable for something else. And we will look in more detail in the logistics process, because we think this is important, whether this all goes together, the packaging and the transport and the storage underground. So this is important. We try to set up a very simple model that simulates that so that we can include it. Then we need to look at additional stakeholder objectives. So there are several topics like criticality, environmental impact, and so on. Here we are confronted with the same problem. We need to find the good order or the good priority of topics to be addressed. And of course, once we say, well, we want to look at this, and so we also need the proxy models so that we are able to assess this. And of course, we also will always strive to do the benchmarking, confirming the results that we have obtained with the simple models, with the detailed models. And this will be the future of this RD&D project. Thanks.
So, good afternoon, everyone. It's quite a pleasure to be with you and to share the evolution of the Belgian concept. So we are still at the conceptual phase. And I have a big challenge is to keep you awake this afternoon, because I'm one of the last speakers, so it's always a challenge, and I hope I will succeed in it. This will be my success criteria for today. So, just a brief history. I think a lot of you knows it already. It's already more than 40 years, so we were one of the first to start, but we will not be the first to start a geological disposal, unfortunately. But 40 years ago, we've started with an underground research laboratory that we've constructed in north of Belgium, which is called ADES. And that's important this year, because this is 40 years of EURIDIS, so our underground research laboratory. And so we are celebrating it quite this year. So in parallel to these research activities, Andra NIRAS is also performing support to policy, national policy development for geological disposal and for a solution for intermediate level waste and high level waste. And so this is done in parallel to this research work. We have made various important steps, the waste plan, public discussion in 2011. In 2014, we have introduced the law and the Euratom directive in the law in Belgium. And a very important step, not so far as our Swiss friends, of course, but we have a first step in a national policy, which has been decided by our Council of Ministers on the 1st of April of this year, so it's quite new, to start a multi-stage national policy approach, and with the first steps normally having to start this year, beginning of next year, a national debate around the solution for high-level waste and intermediate-level waste, starting from a geological disposal facility. So this is a multiple steps. I will not enter into it. Important to note that it's irreversible at each of these steps. And the final steps will be the national policy for the site selection. So we are still 15 years, I think, before we have this site selection, but it's already a good step and bringing also some dynamism, I would say, in the development of our project. So basically now we can jump into the optimization. And optimization is written in the Belgian law. So in Belgian law, we find three interesting things and important things. First one, we find iteration. So we have to iterate at least every 5 years on a disposal design. Why? In order to be able to calculate the costs and to apply the principle polluter pays. That's the first step, iteration. The second step, which is already also in the law, this is the optimization. And we have to optimize that for 4 different pillars, which are the pillars on rough NIRAS. This is economical, techniques, environment, and safety. And above this, in on-graph NIRAS, that safety is first, but we have 4 pillars for the optimization, and this is in the law. And the last one, as I mentioned, we have no real national policy, I could say, so we have to start with a reference scenario, and we consider that we will construct in the geological disposal facility in Poland the rated clay. So this is the host rock of the underground research laboratory. And in Belgium, it means boom clay or EPO clay, so between 200 and 600 meter. And for cost analysis, we consider 400 meter. And moreover, we consider one site for the intermediate level waste and high level waste. Just to give you an idea how we are working, for the intermediate level waste, that's mostly legacy waste, around 9,000 cubic meter. And those will be placed in monoliths, what we call monoliths B, so a truncated cylinder with a height of 2 to 3 meter. And one of the major functions of the thickness of concrete is to provide radio protection. So it's a maximum of 25 microsievert per hour at 1 meter distance. And for the high-level waste, we have the same principle of radio protection, and we used, and you can see that on the right bottom of the screen, a super container. And in the Belgium scenario, we have a mixed scenario, so direct disposal of spent fuel, and also disposal of vitrified waste coming from the reprocessing of high-level waste, and we use super container to put that in the geological disposal facility. So we have to first make a little bit history. In 2003 till 2013, we've started with the first geological disposal concept, which was mostly inspired by the underground research laboratory. So it was a fishbone skeleton that you can see here on the screen with 2 parts. On the left side, this is the intermediate level waste, and on the right side, the high level waste. The disposal gallery are perpendicular to one unique access gallery, and each of the disposal gallery had a length of 1,000 meters. What you have to note is at the center, you have the waste shaft, and at the 2 extremities, you have the ventilation shaft of intermediate level waste and high level waste. And also what you have to know, and this is still the scenario right now, we first build, then operate, and then close the intermediate level waste part, and then we do the same for the high level waste in a sequential phase. In 2000 till 2013, we consider only the long-term safety as the main driver for the design. That's the first point. And the second point, we consider at that time only reprocessed waste, meaning spent fuel reprocessed, and so only vitrified waste in the design. However, as I mentioned, in bylaw, we have to make iteration. And in 2018, we've decided to change our way to make iteration. So not only to take into account the long-term safety, but we then focus on other aspects. And we start within the real optimization process, and we divide these steps into 2 main steps. First step was performed between 2013 and 2018, so step 1, where we take into account the operational safety. In the second step, between 2018 till 2022, we enter into a multi-criteria assessment, so an holistic approach. We have already discussed about that this morning and right now. So we've decided not only to take long-term safety and then operational safety, but try to consider most and more parameters in order to make our design evolve and to make it more optimized. So I will go in this next part of the presentation in these 2 different steps. So first steps in 2018, we've decided, as I mentioned, to increase the operational safety or to take it into account. This is what you can see on the upper left corner on the screen. And also to optimize the steel quantity by minimizing it and so reducing the gas problematic. Moreover, we moved from a full reprocessing scenario to a mixed scenario, so vitrified waste plus direct disposal of spent fuel. And we include the reversibility and retrievability requirements from the Euratom directives, which are now in the Belgian law. And we've performed the work together with Andra, Tractable, BG Tech, all together in order to optimize the layout, taking into account these parameters. So in order to include this operational safety, what we have done, we have performed quite different technical analysis, ASIT analysis mostly, for two phases, the construction phase and the operational phase. From this ASIT analysis and workshop analysis, for the construction, we arrive at the conclusion that three constraints have to be taken into account, considering the pooling in the rated clay geomechanical parameters. The first one, based on the return of experience from the construction of the Metro of London, we concluded, together with our contractors, that we have to respect a ratio at the crossing between galleries of 2, minimum 2. Then we had to avoid X-crossing between the galleries, so between the access gallery and disposal gallery, and so we shift from a X-crossing to the T-crossing. That is the second constraint. And the third one is that it was not feasible for our pooling the rated clay to directly construct the shaft inside in the intersection of the access gallery. So that's three constraints related to constructional aspects and operational safety of the construction. Concerning the operational safety of the operational phase, we had two more constraints. The first one, so remember this fishbone skeleton with only one access gallery. We doubled the access gallery in order to provide two escape routes to the workers in case of incidents and accidents. So that was the first constraint, the doubling of the redundancy of the access gallery. And the second constraint, we introduced the concept of safety distance inside our geological disposal facility, meaning a safety distance of 400 meters. So it has two impacts. First of all, the disposal gallery length go back from 1 kilometer to 400 meters. That was the main impact. And the second one, as we have doubled the access gallery, we had to put and construct crossing passage between this access gallery every 400 meters. In order to integrate these 5 constraints, so 3 for construction, 2 for operation, what we have done, we have made a multi-assessment of different options, and that's what you can see on the screen. Unfortunately, I have not that much time to go inside all these different options, but the idea, we've worked together during mostly workshop activities and technical preparation work in order really to consider different options in order to integrate those constraints. And you can see on the screen, part of them have 2 access galleries. When they have access galleries, you have crossing passage every 400 meters. We have reduced for each of them the length of the disposal gallery. So we have really integrated the constraints. And we arrive at the conclusion that the type C was the best one in order to, and that's the results of this first step, or this first integration optimization, to arrive to the geological disposal layout of 2018, where you can see that we have implemented those constraints. So we have 2 access galleries, crossing passage between all of these access galleries, reduction of the disposal gallery length to 400 meters, and the construction of the shaft away from the access gallery. And as you can see also on the layout, last but not least, all the X crossing are now shifted to T crossing. So that was the first step of 2018. That was the step. So, as I mentioned, we have also optimized the quantity of steel at the same time, so also in 2018. And to do that, we've performed a few finite element simulation on 2 aspects, the current section of the access gallery and the current section of the disposal gallery. That's the upper side of the screen. And at the lower side of the screen, we've performed 3D finite elements with soil structure interaction to model the real behavior, to model at least the behavior of the crossing between access gallery and disposal gallery. From this finite element analysis, so we have really modeled the different phases of the construction, we arrive at the conclusion that it was not required to have steel reinforcement in the current access gallery and disposal gallery sections. So it was quite good news. We could reduce quite a lot the quantity of steel. But at the intersection, we had to reinforce locally over a distance of approximately 15 meters. We had to reinforce by reinforced concrete the crossing between the access gallery and the disposal gallery. So this was the second main important aspects of the GDF layout 2018. As I mentioned, we are now in 2018 till 2022. We are now performing the next iteration. So remember this 5 years maximum time between iteration. And in order to do that, we start again, but now with the layout of 2018 to make it evolve. And we have rather changed the way we approach the work. First part, we've performed long-term safety. Then we go to operational safety. Now we had the impression that we had to have more complete and overall approach to take into account different criteria. And so we jump from this parameter per parameter to an holistic approach and to use an optioneering process that we have to develop together with Jacobs Engineering. Moreover, we've taken also into account the peer review that was performed by the waste producers in order to integrate the peer review and the optioneering process in the optimization. Just to mention, the peer review from the waste producers indicate that the main important parameter for cost analysis was the length of the gallery. Of course, we have reduced quite a lot the length, meaning that we have to increase the access gallery, the number of disposal gallery length, and the number of T-crossing, which means an increase on the cost. And the second parameter was to change or to reassess the margins or contingency on the cost. So this is what we have done in order to make this optimization. So this is the second step of this optimization. In 2018, we developed an optioneering process, and we had 5 requirements for this optioneering process. The first one, that has to be logical. So meaning when you have finalized this exercise, at the end of this exercise, you take the report and you arrive also at the same conclusion. We hope so, at least. The next one, it has to be traceable. So we have to be able to take into account and to justify why we went from one design to another one and to trace it and document it. So people after us, because it will take still time, can find back the justification why we have selected these choices. It has to be robust. So meaning that when we change the layout, we have to be sure that any parametric study or small variation will not arrive to a completely change in the design. It has to be systematic. So it means and I will just show here the example on the length of the disposal gallery, but it has to be applied to each of the modifications that we will take into account. Number of shafts, position of shafts, operation, mechanical aspects. So we have to apply that in a systematic way. And last but not least, as I mentioned, it's a multi-criteria assessment, so taking into account different parameters. So in order to do that, we had these requirements. We have followed principles in 5 stages. So the first stage, I don't know, one of you has spoken about that in presentation. We have first well-defined what we want. So it's good to say we will make optioneering, but what are we trying to optimize? So that's really the first step. What are we optimizing? And what is the scope of this optimization? The next step is a long list option. So we enter in stage B, and then it's like brainstorming or very creative workshop that we have to do. And why is it important? It's important to be open-minded in order to detect as much possible all the options that can exist. Why? To be sure that at the end we have covered everything and we have made a good screening to justify the choice of the options. Based on these long list options, we have screening criteria, which are mostly based on policy, based on a regulatory framework, and also best available technique. So my colleague Christophe has spoken about that this morning, but not entailing excessive costs, of course. That enables to reduce the long list option to a short list options. And then based on the short list option, we make a qualitative and quantitative assessment based on criteria, what we call also attributes. And those attributes are built around the 4 pillars of on-draft NIRAS, or 4 pillars of the law. So you remember in the law, science and technique, economy, ethics and society, and environment and safety. Ethics and society for a conceptual design is quite difficult, but we have really investigated reversibility and recuperability. Then at the end of the stage C, you are able to define 1, 2, or 3 options that can be considered. And then we performed a parametric study or sensitivity study in order to show that the results that we obtain are robust and that the conclusion can resist to a sensitivity study. And then we make the report in order to have the traceability. So that's an example of the application of this optioneering on the disposal length, disposal gallery length. So on the left side, I've made a shortcut, so I don't show you all the long list options. It's quite 10 to 11 different options. So we have considered 5 options in the short list option. The upper left, it's the design of 2018 with disposal gallery length of 400 meters. And then we've considered different gallery lengths from 500 meters to 800 meters. Then to 800 meters to 1,100 meters. And the last one, it's a very special case that we have considered. It's a disposal where you have a disposal gallery length of 50 meters. Why 50 meters? It's a very specific Belgian case, I would say. We are using as backfill cementitious material meaning that we can only backfill 50 meter by 50 meters. So when you put disposal in the geological disposal, you have at that time to backfill with cementitious material, which means at that time that you reduce the reversibility possibility. And so the idea of the last design is to take this disposal gallery length of 50 meters in order to leave open the reversibility as much as possible. So we had these shortlist options. We had criteria, 20 criteria based on the 4 pillars of on-draft NIRAS. And what we are doing is technical notes preparation, and then during workshops with our own experts, but also the experts from the waste producers. And that, I think, was quite challenging, but also interesting because we had different aspects from different point of view, I would say. We arrive on the right side of the comparison, and that's a typical example of results that we have. We have a score of these 20 criteria, and we have a total score of the different options. And what you can see on the screen, basically, first of all, on the left side, the 50 meter are quite bad, but are quite bad really for cost reasons, because it costs quite a lot to construct all this T-crossing. And one or the best solution would be between 800 meter and 1200 meters. So the both columns that you have there. And we have considered the conceptual layout and design that we had to go back to 1000 meter, but implementing a rescue chamber. So we have now mobile rescue chamber inside the disposal gallery length to ensure the operational safety. So basically, in summary, this is an iterative process by law. Optioneering, we optimize it. We start, and the first step in 2018 to include the operational safety. Then we arrive, and this was with the optioneering, to the layout of 2020, with a maximum length of disposal gallery of 1000 meters. In 2022, we've made a second iteration on the operational safety, because we were still in discussion with the waste producer for the cost analysis. And so we analyzed the operational safety and the return on experience from different layout from different countries in order to detect the decent features that we had to have. And the next step, so remember these 5-year steps, it will be to perform a detailed operational safety, taking into account and including the optioneering process that we had developed. So in conclusion, what we can say here, we are still at a very conceptual level. We have still no national policy, or almost no, but a first step still. So we have to be positive, of course. But we are already, even at the conceptual level, already starting this optioneering process, not meaning that we are trying to reduce any cost, but we are trying to find the good equilibrium between all the different parameters, taking, and as I mentioned before, knowing that the safety is one of the most important principle from the on-draft NIRAS. But starting from this optioneering, we could progressively iterate by integrating the operational safety, but also building a methodology which is able and systematic, robust, and traceable in order to make evolve our design through the lifetime of the design. And when we go to the next step, we can continue, I hope so, with the same methodology. And finally, I would just like to finish with the 3 last bullets, which are the main challenges ahead of us. The first one is the design integration, or the design iteration that we have to do on the detailed operational safety. And that's a request of the federal authority, but also that's just something that we had to do. The next one is to implement the first step of the national policy. So to implement this national debate and to perform it in a good way and to arrive at the conclusion, hopefully, that we go to the geological disposal. And the last point, and to mention, we are busy to write our first safety and feasibility case, and hopefully we will have it for 2025 or 2027, but that's in the pipe.
Hello, everyone. I know that you must be exhausted. You have been force-fed with so many presentations. I try to be short, brief, and relevant. It's a challenge. Oh, I'll start with a joke. I have to pay tribute and acknowledge the contribution of my co-authors, and more particularly to Gilles Armand, who's a high-profile geotechnician, which I'm not. And I must say also that in a world of dreams, you would get rid of scientists and scientific people, and you would also get rid of operational safety and long-term safety specialists. But in the real world, you have no choice. So Hooray for the scientist. Okay, so just a bit of introduction first. You might have seen these figures or sketches before. You have on, so I'll see if it works. Yes, it's working. So this is the position of the CIGEO project on the eastern part at the fringe of the Parisian basin. Oops, not so convenient. You have here the ZIRA, which is the zone inside which the CIGEO underground repository is positioned. You have a 3D view showing the main faults and the formation. And you have an overview of the project. And you have in blue the zone which is for the repository. It's not so convenient. For the repository, part dealing with the disposal of the vitrified waste packages. And you have here, you have here a sketch showing the microtunnels inside which the high leaf waste are positioned. The HLW packages are placed in a series of microtunnels, which are horizontal, and drilled, excavated from the access drift. The microtunnels are cased with steel liner. That was selected for emplacement and also for retrievability. We have no choice. We must be able to retrieve the packages over the duration of operation. That's about a secular period. Okay, talking as a project engineer again, what is my concern? Technical, economical objectives, if you allow me, main core of optimization, my point of view, but I'm a project engineer, so that could be discussed. For reducing the technical challenges and the economical consequences, you have to reduce the disposal underground footprint. As mentioned in many occasions during this symposium, the host rock formation is a scarce resource. So you have to preserve as much potential for other uses, including, for instance, the extension of the chronicles, the extension of the inventory. You must reduce, by consequence, the cumulative lengths of disposal cell access drifts. And for that purpose, you must reduce the spacing between the disposal cells. What are the scientific and long-term, those two guys, they are too much. The scientific and long-term safety objectives: preventing host rock fracking induced by thermal loading. This thermal loading being generated by the thermal power of the high-level waste packages. For that purpose, you must improve the geotechnical knowledge and host rock behavior under thermal loading. And for that purpose, you have to plan in vitro and in situ tests at various scales of time and space. And that's the purpose of the presentation. First of all, design criteria. The disposal packages should be placed in a network of parallel dead-end microtunnels, as mentioned. The heat emitted by the waste will generate in the Calov-Oxfordian claystone a temperature increase and a pore pressure buildup. These phenomena are due to the differential thermal expansion of the Calov-Oxfordian skeleton and the pore water, which is connate water. The generation of a transient mechanical field can lead to fracturing, extension, and shear at multiscale. That's a point which I will talk about a bit later. What is the extent of that fracturing? That's a real challenge. So design criteria and long-term safety requirements are defined to preserve favorable properties of the Calovox-Fordian formation by essence, which means that the maximum temperature at contact of the host rock is limited at 90 Celsius, and we must at all time prevent damage, fracture initiation in the rock. This is what we call the THM criterion. Oh, here you have a more practical view. I'll try again. Yes. So this is an overview of what could be done. In red, you have, okay, you can see what is measured at mid-spacing between two disposal cells. You have a phenomenon in which the heating, depending on the spacing between the disposal cell, could provoke an uniaxial tensile strength, inducing subhorizontal damage cracking. So this is the challenge. How can you predict such an event? Okay, just a more scientific illustration of what's going on. The vertical extension is a challenge because we do not know what is the real tensile strength of the rock. So we take for granted it's nil, but of course in the real world it will be different. And the lateral compression and the vertical extension will combine and provoke a deviatoric stress increase. So this is what is illustrated in here. So the challenge is to find a way to upscale from sample to repository scale. Well, the first type of work is to go on samples. The samples are cored inside the host rock formation. Then you have to go to a one single microtunnel and then at a repository scale. And you have to extrapolate from what is collected at the scale of the underground research laboratory. And you have to extrapolate to what would be the relevant data for a repository footprint of about 8.5 square kilometers. How to take into account geological variability. And when we say geological variability, you are talking about petrofabrics, the Young modulus, the conductivity coefficient, and maybe also the fact that there will be a topographical variation from one part of the surface installation to the other one. So the overburden will be different from one part to the other one. At the time, the limited data which we have are provided by geophysics, as illustrated in here. Is it working this time? Great. So the first results obtained were at sample scale. You have here a view of what was obtained by pressurizing tests on Calovox-Fordian samples, which, as I said before, are cored perpendicularly to the subhorizontal stratification orientation. This is the way the host rock is stratified. And you can observe that the stress path conducts to the apparition of one horizontal fracture. The tensile stresses vary between 0.5 and 4 MPa, and this is coherent with the results obtained by traction tests. Next one, a new attempt. My goodness. Okay. Okay, here you have an overview of what has been carried out over a duration of some 15 years with various measurements made on boreholes, measurements made on a demonstrator, what is called ALC 1604, which is a prototype disposal cell built in the URL. And finally, what was done, it's what a thermal fracture test, which is called CRQ. in order to find a representative stress path. Okay, objectives and results. Disposal cell experiment. Demonstration tests are carried out at full scale for a microtunnel. In situ test enables to increase the knowledge on THM behavior and verify the accuracy of numerical models at full scale. And you can find that pressurization coefficients are similar to the one measured at small-scale tests. It means there is a good coherence between full-scale test and sample test. And from a theoretical point of view, there is a good reproduction of the pressure increase within a poroelastic approach. And concerning the CRQ experiment, which is the most significant test carried out so far, we could manage to evaluate the host rock THM behavior under thermal loading, as it could be generated in CGO at mid-space between two disposal cells. We could pursue the thermal loading until rupture of rock. So yes, the rock is fracking with heat. And we could observe the volumetric deformation generated by the heat transient and the fracking phenomena. And we need a second test to confirm that the results and the value obtained are again observed. As a consequence, we may say from a theoretical point of view that the thermoporoelasticity model allows a good prediction of the THM behavior at the borehole and the disposal cell scale. And we can say that the thermoporoelastic approach overestimates the effective stresses compared to the other models. So, in a way, this is what is shown in red. The thermoporoelastic approach is robust for the design of CGO, we're on the safe side. But of course, it's a penalizing theory. So I was talking about the need to go for multi-scale investigations. So phase A, laboratory measurements on the samples was done, will be continued. Geophysical measurements on the boreholes was done, will be continued. And wave propagation investigation at the site scale, 3D high-resolution impedance, to be evaluated more thoroughly. And that will be done in, say, 3 to 4 years with a new campaign of geophysics. And spatial variability will be determined by this 3D impedance campaign. And we shall have also additional boreholes, which will be excavated at the periphery of the Zira zone. In particular, I was talking about that the Young modulus on Zira may vary from one place to the other for three reasons. The geological variability in line with the petrofabrics, the deepening of the host rock. The host rock is deepening when you go north, and also the host rock thickness is increasing when you go north. So you have to take into account these parameters. And also, I was talking about the topography of the overburden formations. So all this implies that most likely the Young modulus is varying from one part of the Zira to the other. And as mentioned before, since those data are not available, data and uncertainties have been considered for the current design with a very cautious approach. Concluding remarks. The pore pressure increase is due to the difference between thermal expansion of pore water and solid skeleton. That is clear. The Galovo-Oxfordian formation is relatively rigid. The low permeability of the Calavo-Oxfordian formation is confirmed. That's not a surprise. That was the reason for selecting such a host rock. And of course, we have to take into account the boundary conditions, which are linked to the design of the disposal cell network. In terms of thermal damage, we are trying to check if there would be a modification of the Calavo-Oxfordian mineralogical components with the temperature increase or the temperature transient. And so far, we have not found any significant modification as a function of the applied temperatures. The possible localized damage, the fracking, induced to the excessive pore pressure increase is certain. High value of pore pressures can be reached in line with the thermo-hydromechanical pressurization and boundary conditions. The most influenced parameters are the rock stiffness, the Young modulus I was talking about, water permeability, thermal conductivity. And so far, the thermoporoelasticity model is an accurate model for the design. Okay, ongoing works. We need to consolidate the data and to reduce remaining uncertainties, even if for the CGO licensing application, a conservative design approach has been already chosen. So we shall continue works on small scale THM behavior and processes. We shall try to find less conservative failure criteria. And we shall try, of course, to upscale the parameters from sample URL scale to the scale of the repository area. And one very important bullet is the last one, assessment of consequences of a possible damage. So far, it is very complicated to forecast what would be the extension and the orientation of the fracking. Will it be horizontal? Most likely. Will it be localized to a few disposal cells, or will it affect the total disposal area? Nobody knows. And how long will it last? Most likely, this phenomenon will disappear with the thermal cooling, with thermal decay. And if so, is it that important? When we talk about the EDZ, the excavation damage zone generated by the works, the excavation works, we have shown that sealing, hydraulical sealing, will take place. Here we talk about a sub-horizontal fracture with a limited expansion, which takes place for a limited amount of time. Once the thermal decay is taking place, of course, the thermal transient phenomena will disappear, and of course, this fracture will close. So the sealing capacity of the Calavo-Oxfordian is a very good property. It is applied for the safety demonstration for the EDZ. It can be also considered for the sealing of the Calavo-Oxfordian after fracture generated by temperature. So this is part of the work which has to be carried out in the years to come. Okay, you have seen this slide presented by my colleague Pascal Levert during the opening session. What is at stake? At stake is the main disposal panel, which is composed of the high-level disposal waste to be constructed and operated in the years 2080. In the meantime, we have a very small disposal panel for high-level waste packages. We have some 20 to 25 disposal cells, which will be constructed during a first period, what we call the inactive period and the active period. So it means that we shall have some, say, about 20 years of observation of the disposal cell in the pilot phase. And over that period, until 2080, we shall have some 30 more years for observation of what is going on. It means that we have a lot of time to consider if the design hypotheses regarding THM behavior are good, if the HLW pilot zone concept is relevant, and of course, we shall take into consideration work activities and nuclear operation to see if the anticipated phenomena are relevant. Okay, and in the years 2080, as Pascal Levert mentioned, we might have a totally different design. For instance, shall we be still with steel-cased disposal cell or with other materials? And will the disposal package canisters will be made of steel or of a different material? We do not know. And of course, by that time, we shall have a new inventory. We shall have new data about the thermal decay. We shall have new data coming from the waste generators regarding the period during which their interim storage can take place. So it's open. And what we are doing now with the pilot phase is a careful approach. And I would say we are on the safe side. From the investment or expenditure point of view, building a disposal panel for 20 disposal cells is a minor impact, a minor figure. And it can generate significant savings for the big thing in the years 2080 when we have updated data. Okay, that's the last one.
So last official action for this afternoon, I would like to invite Tina to provide a summary of the 2 days symposium, but also to close the meeting, sadly.
Yeah. Hope it works. Yeah, it has been very interesting 2 days and hearing various kinds of presentations. So I try to make a summary of them. So excuse me if there's something that I don't mention. I cannot mention it in 20 minutes, what we have been hearing for 2 days. To start with, we know that we have considerable scientific and technological knowledge base today. And we have sufficient and appropriate, robust knowledge base to facilitate our licensing and construction of the geological disposal facilities. But still, it is very important to maintain, enhance, and increase knowledge throughout this incremental development, operation, and eventual closure of disposal facilities. So, which will spread over many decades. That has been said by Irina in one of our presentations. And within these 2 days, we have been concentrating on the central pillar of the vision of the IGD-TP strategic research agenda and the vision. So to optimize and industrialize our geological disposal facilities. I take some main messages from each of the sessions, mainly prepared by the chairs. So thank you all the chairs, and if there's some of my additions, then they are in there. So within the role of optimization in selected national geological disposal programs, we have heard that the optimization accompanies the entire disposal program. So it is not only relevant during the implementation phase, so in each of the phases. And topics and drivers of optimization may change during the different stages of a disposal program. Optimization is supported by a stepwise licensing approach that allows for adaptation to optimized solutions. And then for early stage programs, international cooperation is a key component for optimization. So early stages or small inventory stages, it is not most optimal to do everything by themselves. From lessons learned from optimization in large infrastructure projects, we heard many very interesting topics that we can benchmark. And that is something that we actually have been doing in many programs, benchmarking the existing industries and existing know-how from some other fields of expertise. So key messages concerned the various tools to visualize what excellent looks like, what is our aims, what are we targeting at. Similarly, the use of success factors and requirements to drive cooperative solutions between client and contractor. So communicate, define your targets and make sure that you have the common targets. Also, the importance of taking decision makers, communities and regulators on the journey and recognizing the need to deliver broader benefits to local society through associated development. Everybody is a stakeholder in this field, I would say. Then we go to the technology and material optimization, chaired by Joakim. DGR is a long-term project in which there is continuous need of optimization, improvements of the components and activities related to the radioactive waste management. And issues as optimization of cost and time schedules are to be taken into account as the implementation approaches. Robustness of designs, components is considered as essential for the development of a deep geological repository. So these were the main messages we picked from these two sessions, and two more: integrating optimization for safety, chaired by Peter. What is the rationale behind the optimization? We heard the question raised. We heard integrating optimization and the safety case, Alara and Sahara concepts and terminology, and graded development of geological disposal and safety case toward optimized solution. And in the last session, global optimization approaches, concepts and numerical applications, chaired by Ingo. We heard the definition of the optimization. That was nice to be heard at the last session. To make something as good as possible. We heard about thermal aspects, which are the key to develop a safe disposal system. We need to consider the entire nuclear backend. And optineering was a new term for me at least, and how its application enabled to optimize the overall layout of the cheap geological facility. And then optimization of thermal dimensioning of the CCO project. So these very various, very interesting presentations we heard during these 2 days. So many thanks to all of you presenters, chairs, everybody, the audience, everybody behind the presentations. One more reminder for the IGD-TP strategic vision and our strategic research agenda that was published in 2020 and can be found at the webpage of IGD-TP. We have topics of a list of our priorities that we see. So these are only the topics, quite broad as you see, but there are several topics, issues under these topics that we highlight are the main interesting, main remaining points that we within the IGD-TP would be interested in to supporting. So some reminder of that. Then we get to the very interesting part as well. So I have here something, yes. So as the best poster selected by the IGD-TP Symposium scientific focus group, I named the best poster, and I would like all the presenters or everybody who has been doing the poster to raise up, and maybe one of you or maybe all of you then can come up and pick your present. So the best poster is Safety Case for Disposal System Optimization, Low and Intermediate Level Disposal at Vatapi, Hungary. So Peter Molnar, Gila Danko, Balint Nos and Tamas Takac. Thank you very much.
Thank you very much. That's a pleasure.
Thank you. Thank you. Thank you. Yeah, so some remaining works. I would like to thank once again the chairs, the presenters, for the posters, the technical stuff. Everything has gone without any scandals, any panic. So everything has been perfect from the arrangements, and also, of course, the audience that you have been active, commenting and giving nice questions. So. Also, thank you for the scientific focus group for planning the program. I have heard that many of you have thought it's been interesting and broad. And NAGRA for organizing and hosting the symposium. So here I would like to ask Irina and Ingo to step up. And maybe some help from Johanna. Yeah, so not only for hosting such a nice symposium, but also for taking such good care of the IGD-TP chairmanship for the two of you. And I think it's nice to continue from this on. So thank you very much.
Thanks a lot, Tia.
Thank you, Ingo. Okay. So we have we have prepared some Finnish design for you to take on, so you remember us every time.
We will not forget you.
Is it chocolate?
No.
Thank you.
Ingo.
And something more. Also, I would like to thank for the arrangements, Tamara and Annika. Please come here. So Tamara, you have been so helpful with the IGD-TP, the secretariat, and we really appreciate your work. So now we have then continuation with Erika, but everything has been so well. So thank you very much.
Thank you.
And Annika, thanks. Okay. Annika, thank you for all the arrangements. You have been taking so calm everything, and everything has been gone so well. So
Yeah.
thank you.
Thank you.
The final picture today.
And here is also a small memory. It's almost like a copper canister color at the scarf. and then next time when someone is asking if you would like to take some responsibility in the project, you should consider whether it's too hot to handle.
Oh, sorry.
Whether it's too hot to handle or not. So Finnish licorice, strong one. Okay, so that's. And thank you, Tamara. That has been great. Annika. Thank you very much. Yes. And also the same thing. And of course the Finnish rice bread. Thank you.
Thank you very much. Thank you. And thank you, Johanna, for helping me with this. So one more reminder, next week, Thursday, we will have a webinar, and we will still hear some more perspectives on the role of optimization. And we will have very high-class panelists there, Stefan Meyer, Chris Boyle, Jaakko Leino, Reinhard Kner, and Pete Zuidema. So mark this in your calendar, please. And with this, I would like to thank you, everybody, once again, and have a nice journey to the Grimsel, to the wherever, or back home. So thank you very much, and have a nice journey.